Welcome everyone to the video of the ANN workshop. We would be creating an artificial pigeon brain and train it such that it recognizes some images that we give in for testing. So before we start with the tutorial, we would be making use of Pytorch. So I would introduce to you what Pytorch is. So Pytorch is a scientific computing package that builds on the NumPy library to allow for the use of GPUs. It incorporates deep learning capabilities while maximizing flexibility and speed. So GPU stands for Graphics Processing Unit. You'll also see people referring GPU commonly as graphics card or video cards, and every PC uses a GPU to render images, video, and 2D or 3D animations for display. So let's start working with Pytorch. Let's do some basic operations. So to start with using Pytorch, we first need to import the library in Python, and we import it using a statement called import torch, and I will run this line of code for Colab to know that now we're making use of the Pytorch library. Now we'll be creating some tensors. So tensors are n-dimensional array that can be used with the GPU to accelerate computing. And there are various ways to use tensors. Some of the examples we would be discussing now. So first we start by initializing a random tensor. So we make a variable x. We call the library torch and we use an inbuilt function called rand, and it's used for generating some random numbers. And in the bracket we have 4, 3. So here 4 are the number of rows and 3 is the number of columns. So a random set of numbers with 4 rows and 3 columns would be given as an input to x, and now we have to print x so that we know what values are given into x. So let's run it and see what values we get. So here you see these were the values that were given into tensor. It has 4 rows and it has 3 columns. Now let's do another operation where we would be initializing a tensor with zeros. So there's an inbuilt function called zeros. So we make the variable x and we say torch.zeros again with 4 rows and 3 columns. So we should be getting a tensor which has 4 rows and 3 columns all with zeros. So if we run it, here you see there are 4 rows and 3 columns filled with zeros. We can also initialize a tensor with data entered manually. So if we give an input as 2.1, 4.0, minus 5.2, so you would get a tensor having this value rather than giving it randomly or loading it with zeros. We can also manually enter the data. So let me run this block of code. Here you have your tensor, you have 2.1, 4.0 and minus 5.2. You can also initialize data from the NumPy library. So to use NumPy library, you do import NumPy as NP. You could also leave it as import NumPy, but then you would have to write data equals to NumPy.array. So just to make it smaller, we just use an abbreviation as NP so that whenever we want to call NumPy, we would just be using NP everywhere. So now we are creating a data using a NumPy inbuilt function called array, and we manually fit in data called, fit numbers like 2.1, 4.0, minus 5.2, and then you print the data. So here you see this is a NumPy array having 2.4, 4.0, minus 5.2. And now you can also make this, you can also, like the data that we have over here, we could also make it a tensor and print that tensor. We can print that tensor. So you would get the same set of values again, 2.0, 4.0 and minus 5.2. You can easily convert tensor to NumPy by just writing x.NumPy. So here we have x as a tensor. So if you make another variable called x underscore numpy, and we write x dot numpy, so it will convert the previously tensor to now numpy, and when you print it you have the same value as the same array as we had in our first output line. Now how to obtain the size of a tensor data structure. We had used a statement called torch.zeros 4, 3, so it's just giving 4 rows and 3 columns of zeros, and now if we want to see what the size of that is, it would be the same as 4, 3, because this is the size that we had given to it, like 4 rows and 3 columns. So we can also perform various operations like addition, multiplication. So it's just the way you do addition x plus y. So here we're doing random values of 4 rows and 3 columns, and we are making another variable 4 rows of 3 columns which is only filled with ones. So now when you want to add x plus y, this is the value that you would be getting. Now we can also multiply it the same way, and instead of doing x plus y, we would just do x into y. So you see what we have is a multiplication already done. Now we want to provide output tensor as argument. So what we're doing here is that we're taking a variable called result and torch.ones43. So here it's creating again a 4 row 3 column with ones, and we add x and y and output result. So this is another way of adding x and y and giving out the result in the form of ones. So if we print out the result, here you see it's all again ones as in a tensor. You can also resize and reshape tensors. So we make again a random 4 row 3 column tensor, and we can basically just put in like you see, we want to find the size of x, we want to find the size of y, we want to find the size of z. So we have 3 variables here, x, y, z, and you see that the first one is given the size of 4 and 3. The second one is given x.view12. So it's basically x but given a size of 12. So now the new size of y would be 12. And now you see x.view is -4 and 3. So now x had previously 4 and 3, and now when you input -4 and 4, you would get a torch size of 3 and 4, and here size -1 is inferred from other dimensions, so you can write it in any other way as well. Now if you want to convert one element tensor to a Python number, so you can just do x is equal to torch random 1, you print that value, and then you print x dot item. So we have a random we have one random number which came out to be 0.1371, and you have tensor around it showing that it's a tensor element. But now if you want to turn it to a Python number, you just write x dot item and you get the same value without tensor written around it. So let's go a little bit more deeper and we look into what automatic differentiation is. So the Pytorch AutoGrad package allows for easy computation of derivative, and it is handled automatically using a define by run framework which works as you write your code. So to enable this feature, you need to set the tensor attribute .requiredGrad to true, at which point it begins to track all operations performed on it. So after your computations have been completed, you can call .backward. It's an inbuilt function, and all the gradients will be computed for you. And the gradient for each tensor will be stored in the tensor attribute .grad. So each tensor has a .grad_fn attribute which just references functions that it has created. So let's look into an example. So here we want to do some computation of gradients. So we just make a random variable for 3 rows, 3 columns, requires grad as true because we want the gradient, we want the computation of gradient. So we just set it to true, and now we print x, and then we perform some operations like we make y is equal to x plus 10. So whatever value you get here, you just add 10 to it, and now we take another variable as y into y. So whatever value you get here, you just multiply it with itself, and now we take another variable out is equal to z dot mean, and we print z comma out. So now if I run this statement, you would see x. First print statement was x, so this was the random set of values that were given by the rand inbuilt function, and then after that all these operations were performed, and now we want to print z comma out. So out is basically like the mean of z. So after performing y into y on z, we did z dot mean and we printed out. So this is the value that we get with out. Like to compute the gradients, we do mean, and gradient is basically like the slope of a function. So we take the mean, and now if we want to compute the gradient with respect to the output, we do out dot backward. So as we said here, like after a computation, you want to call dot backward, and all the gradients would be computed for you. So once you have taken the mean, you want to do out dot backward for the gradients to be computed. So now once this is the out value, now when you do out dot backward, the gradients would be computed, and now if you do x dot grad, the gradients would be printed out. So here you see these are the gradients. So now let's get into building on the artificial pigeon brain and making it to recognize some digits. So in this example, we will train an artificial pigeon to perform a digit recognition task. That is, we will use the MIST dataset of handwritten digits and train the pigeon to recognize a small digit, namely a digit that's less than 3. And this problem is a binary classification problem. So binary classification problem is just that we need to predict which of the two classes an input image is a part of. So before starting with the digit recognition task, we first have to load the MIST data, and this data set contains some handwritten digits that are 28 into 28 pixels large. So from Torch Vision, we import dataset and transforms, and then we import a plot from a library called matplot library. So we basically import datasets because we want, from the datasets, we want to use the MIST data. It is already an inbuilt into the library, so we just need to call that data, and for calling the data, you need to import the library first. So we make a variable called MIST train because this is the training data. Okay, so before we jump into the tutorial, I would like to explain a few terminologies. So training data is basically, it's an initial set of data which is required by neural networks or any other artificial intelligence programs, and this acts as a baseline for further application and utilization. This is used for the neural network to learn, to get trained. And then test data is the data where we would be testing, so the model has learned from the training data and now it's been evaluated on the test data. So here the MIST is the training data, and also MIST would be the test data. So in this, we would train from the images that we show it, and it would have to predict the answer for the ones that we don't show. So now we would want to plot the first so we need to load the data first. So from datasets.mnist, we take the data. This is training true, so it's a training data, and download is not really required. So yeah, we train true, and now we need to make a list of all there are 2000 images in it. Actually more, but we take up till 2000 so that it can test on the ones that are not shown to it. So this is indexing, and it starts from 0, so 0 until 2000. So all the first 2000 images would be loaded into this in the format of a list. And okay, so I will run this code so that it knows that it has to load that many images into the variable. And now we have to plot the first 18 images in the training data. To plot the first 18 images in the training data, we have to create a for loop, and for that we take one variable, two variables in fact. So we have k, and then we have image and label. In enumerate MNSIT until 18. So MNSIT has 2000 images, but we would be using only the first 18 images. So now we want to plot all of that, and for that we would call the inbuilt function plot. We have imported it already. So now we do plot.subplot 3 6. So here 3 is just 3 rows and 6 columns, and now it will just show all the images in those 18 sets of in the list of 18 images. So if I run it, here you see these are the images. These are 18 images with 3 rows and 6 columns. And this is the training data. It has been fed into the neural network, so it knows that it needs to learn the numbers from this training data. So let's start with defining ANN forward pass, so that we start with forward pass and later, as I said in my video, we do forward pass first and then we do backprop to see if there are any errors and if we want to change our output according to the output that is actually required. So for that, first we need to do the forward pass, and to do forward pass we would again import torch, import torch.nn as nn. So nn is basically just a neural network, and now import torch.nn.functional as f. So nn module is a real layer which can be added or connected to other layers or network models. So the function torch.nn functional are just some arithmetical operations. We just use it to perform some arithmetical operations on the neural network that also have some trainable parameters such as weights and bias terms. And then again we call torch vision, we import datasets transform, and we also have the matplotlib to call plot for plotting the images. The last import statement is torch.optim as optim. So torch.optim is a package with optimizers, and I will tell you how we would use optimizer later. Okay, and we have torch.manual seed, so we just set a random seed of 1. Now we make a class called Pigeon with the NN module, and we have an initializer method and the forward method where we would be doing our implementation of the ANN forward pass. So initializer is just creating some instances and initializing some value to it. So we make self.layer1. So this is a linear, like making the first layer of a neural network which has 28 into 28 rows and 30 columns, and then we have a second layer, which a linear layer which has 30 rows and 1 column. And now we make this is where we have initialized the values, and now we make use of these initialized values in our method where we would be doing the ANN forward pass. So we have another method called forward, which takes in self and image. So flattened equals image.view minus 1 28 into 28. So it's just it's just viewing the image in which has 28 into 28 pixels. It's just giving a flattened view of the image into a variable. And then over here we would use two activation functions. No, technically we're just using one activation function, but we would have two variables. So the first one, we would do the layer 1. We have initialized a linear network on flattened, which would have the image view, and we would call the ReLU activation function, which I've talked about in my second video. I wouldn't go much in depth in this tutorial. Then we have a second activation function. So we're doing self.layer2 on the first activation, and then we return activation 1. And now we may take another variable, and we just equal that to the Pigeon function. So now whenever we want to call the Pigeon function, Pigeon class, so Pigeon is like an instance of the class. So now if we want to use the class, we would, if we want to call any method from the class, we would be using the Pigeon instance. So now what we created is a network that has 28 into 28, which is 784 input neurons to work with our 28 into 28 pixel images. So we have a single output neuron and a hidden layer of 30 neurons. The variable pigeon.layer1 contains information about the connectivity between the input layer and the hidden layer, and it's stored as a matrix, and the biases are stored as a vector. Similarly, the variable pigeon.layer1, a layer 2, contains information about the weights between the hidden layer and the output layer and the bias. The weights and biases adjust during training, so they are called the model's parameters. Now if we want to view the parameters, we would do it as such. So for W in pigeon.layer1.parameter, so if we call the pigeon.layer1, and dot parameters is for getting the output of what the parameters are. And now we would just print W so that we could just get all the parameters that are there in pigeon.layer1. So the parameter contains the following, pigeon.layer1 contains the following parameters. Now if we want to test the network forward pass, so here's an example of using the network to classify whether the image contains a small digit. So we make predictions for the first 10 images in the MNIST training data, and to do that we first transform the image data into a 28 into 28 matrix of numbers, and to do that we use transforms.toTensor. So previously we had from Torch Vision we had imported transform. So transform is basically just to transform the images into a matrix of numbers. So we do transform.toTensor, and then we do the for loop again, and we make another variable which has like the image value, and now we just do pigeon inval, where it finds the inval is basically input value and outval is the output value. So when we do pigeon inval, it finds the output activation given input. So when we're doing pigeon inval, we're basically referring to the instance of the pigeon class. So once you give when we're doing pigeon inval, we're basically just calling the class here, giving inval as the input. So it will go here, it will do the forward pass, and then it will return the activation, and that's the activation that would be given into outval. And now we need to find the probability, and for finding probability we use the sigmoid activation function, which I talked in detail in my video 2. So when we do torch.sigmoid outval, it gives the probability. It returns the activation in the form of 0 or 1, and then now we print the probe to see what value it gives us. It gives a bunch of zeros which are close to 1, some are close to 1, some are closer to 0. So since and why do we get such values? That's because we haven't trained the network properly. The predicted probability of images containing a small digit is just close to half. The Pigeon is unsure as of now because we haven't trained it yet. And in order for the network to be successful and to be useful, in fact, we actually need to train it well enough so that the weights are actually meaningful and they're non-random values. So to update the parameters, we would be using gradient descent with cross entropy. To update the parameters or the weights, we will first use the network to make predictions, then compare the predictions against the ground truth. To compare the predictions against the actual values, we'll compute a classification error using the cross entropy equation. The classification error, that is how good or bad the prediction was compared to the actual value, is more commonly referred to as the loss, and the cross entropy as the loss function. So the introduction of a loss function makes a problem an optimization problem, which is what set of parameters minimizes the loss across the training examples. So turning a learning problem into an optimization problem is actually a very subtle but important step in many machine learning tools because it allows us to use tools from mathematical optimization. There are optimizers that can tune the network parameters for us, so it's really cool, and we had made an import statement previously as import touch.optim as optim. So here we're just bringing in the optimizers package so that we can use an optimizer from that package. So the gradient descent algorithm we have derived in the last lecture, so is just one example of an optimizer, and for now we will choose a standard loss function for a binary classification problem, which is called the binary cross entropy loss. We'll also choose a gradient descent optimizer. So let's start with some simplified training code to train the Pigeon on some small digit recognition task. So for that we call the optimizer library, and we make another variable called criterion as nn.bce with log its loss. So what this basically does, it's a loss which is combined with the sigmoid layer and the BCE loss in one single class, and this version is more numerically stable than first using a plain sigmoid and then followed by a loss function. So it's just better to combine both the operations into one layer. And now we would make use of the optimizer, and we call optim.sgd pigeon.parameters. LR we would set it as 0.05 and momentum as 0.9. So what is the SGD? So in SGD the weights are updated after looping via each training sample. So here you see our first parameter is used as pigeon.params. It's a iterable of parameters to optimize defining the parameter groups. LR is the learning rate. We would keep that as 0.005, extremely minimal. And momentum is an optional parameter, but we would want it in this case, and we would set that as 0.9. It is usually a float. It's a float value. So now we need to start training the Pigeon network similar to the way we would actually train a real pigeon. So how would we train a real pigeon? We would show some network pictures of the digits one by one, and we would see how the pigeon recognizes the numbers when we ask from it later. So we do the same thing with this Pigeon network. We show the network pictures of digits one by one. We'll see what the network predicts. Then we'll check the loss function for that example digit comparing the network prediction against the ground truth. Which is, suppose we show a number 1 and it predicts 1, so we would see that 1 is the number that we actually want from it. But if we show it 1, but it says that it recognizes it as a number true, as 2, then there's something wrong in how we have trained the data, and that's where we use backpropagation, so that it goes back into the neural network, fixes the errors so that it makes it to predict 1 instead of 2. So yeah, we will make a small update for the parameters to try and improve the loss for the digit, and we'll continue doing this many times, like let's say 1,000 times. So for simplicity, we'll just use 1,000 images and show the network each image only once. So we'll make a for loop again. We'll for image and label in MIST training MNSIT train for 1,000 images. First we had loaded in 2,000 images, but now we would take 1,000 as we mentioned, like for simplicity. So the actual ground truth, like suppose the digit is less than 3. So now what do? We make actual as the torch.sensor label less than 3, and we reshape it 1, 1, and the type should be .float tensor. So now we want it to give an output such that the number is below 3, and now we want to make the pigeon to predict it. So out is equal to pigeon image.tensor image to tensor image. So we call the pigeon class here so that it does the forward pass. It takes in the image, it does the forward pass so that it could make its prediction, and now we do loss equal to criterion out comma actual. And so this is, we see the loss. So the error is basically calculated with the output value minus the actual value. So that is how we calculate the loss. And now when we get to know what the loss value is, we compute the updates for each parameter, and then we make the updates for each parameter, and then we just do a cleanup step for the Pytorch, which is optimizer.zeroGrad. And it is very common to run into errors with changing different data types to tensor with the correct shape. So let me just run this set of code, and now all the prediction has been made with the pigeon. And now let's just see how much prediction it has made. Okay, so now we would just test the updated network pass. We'll see how it has predicted. So let me just run this. Yeah, so now it makes predictions for the first 10 images. We do it such that it prints out only 10 images, and we use the Sigmoid function to again give a probability of how close it is to the actual data value that is given. And we see that it predicts 5, 0, 4, 1, 9, 2, 1, 3, 4, which is the same number that we had shown it previously. So it has given the right prediction according to what the training data was. So we have done a good job in training the pigeon brain. So we'll use the probability 50% as the cutoff for making a discrete prediction. We can compute the accuracy in 1,000 images as well for training the data. You can use it for as many images or however big your training data is. This is just a small example. Now to check how accurate our training data was, we create a for loop again, and for the error rate we would do error by 1,000, and for accuracy we do 1 minus error by 1,000. So we see that the training error rate was only 0.016 and the training accuracy was 0.84. So you see that the accuracy for the 1,000 images were like 98%, which is really good considering that we showed the network only one image at a time. And now if we want to check the validation of a testing data, we do the same thing again. And here we see that the test accuracy was 94% and the error rate was 0.05%. So this is the Pigeon has learned fairly well. It has given out the right predictions. So we can say that we have done a very good job with making the artificial pigeon brain to make the right predictions. So that is the end of our tutorial. Your next assignment would be to tweak some hyperparameters and get an accuracy to something closer than 98, and if more, that's better. So we would want you to tweak the hyperparameters, get a good training accuracy for both testing data as well as the training data, and we would want you to take a screenshot of your entire screen with you writing the code and with what your accuracy is, and just send it to the email which is given below in the description, and then we would choose the best one of you who has got the highest accuracy, and we've got some amazing Amazon Prime gift cards waiting for you. So yeah, make sure to take your time out, understand the assignment, understand what the code is all about, make your changes and improve the accuracy such. I'm waiting to see your code. Thank you.